in this part of the course, we will study field extensions. So what is a field extension? A field extension is just a pair of fields. One is contained in the other. So it's a pair F contained in K, where F and K are fields. Okay, usually we write this field extension in the following visual form. We write the big field on top and we write the smaller field on the bottom, and we link them by a line. So a line going from up to down means that the field at the lower end of the line is a subfield of the field on top. We may also have towers of fields, like a big field E containing a field K containing a field F, and we'll see more complicated diagrams of this kind later on. So this is just the notation for a field extension. Okay, let's look at some examples. We've already seen many examples of fields, so from these we can construct examples of field extensions. So the complex numbers, the field of complex numbers contains the field of real numbers. The field of Gaussian numbers contains the field Q. So this, remember, this is just all complex numbers will form A plus IB, where A and B are rational numbers. And then you could talk about the field of complex numbers, but that's an extension also of the field of Gaussian numbers. It contains the Gaussian numbers. You can talk about real numbers, contains Q. That's another example of a field extension. And here's another interesting example. So you just take Q of X mod x squared minus 2. So now x squared minus 2 is actually an irreducible polynomial in the ring Q of x, and so Q of x mod x squared minus 2 turns out to be a field, and this is an extension of Q. Let's look at a slightly more interesting example. So given a field F, you can start with any field, define F round bracket x to be the fraction field of the polynomial ring Fx. So an element of this field is a ratio of two polynomials with coefficients in f in the variable x. And this is a field, and this contains the field f. So here's another example of a field extension. Fx contains f. More generally, we can talk about multivariable fraction fields. So for example, you can talk about f round brackets x1, x2, and so on. And this is defined as the fraction field of, well, maybe we have, n variables here, of the polynomial ring in n variables. So now you can see some interesting, so you have the field x1, x2, x3 rational functions in 3 variables. This will contain fields of rational functions in 2 variables, x1, x2, f of x2, x3, f of x1, x3. And then here you'll have f of x2, f of x1, f of x3, the fields of rational functions in 1 variable. Now f of x2 is contained in f of x2, x3, and f of x1, x3. F of x1 is contained in f of x1, x2, and f of x1, x3, f of x2, x3, and then finally we have f at the bottom. So this kind of diagram shows the relationships between several fields at the same time. So here we have 8 fields, and this diagram tells you which ones are extensions of which ones. So this shows you the power of the notation that I introduced last time for field extensions. Now suppose we have a field extension and we have an element alpha in K. Then there's a substitution map. So this is a ring homomorphism from the polynomial ring F, maybe I should call it T here, to K, defined by, so this substitution map is, let's give it a name, we'll call it phi subscript alpha, defined by phi subscript alpha of say some polynomial f t is the polynomial f evaluated at alpha. Okay, so this is a ring homomorphism. It's not difficult to see that this is a ring homomorphism from the ring of polynomials ft to the field K. Now consider the kernel of phi alpha. Now there are two cases. Case 1, the kernel of phi alpha is non-zero. Now remember, the kernel of a ring homomorphism is an ideal in Ft. And if Ft is a principal ideal domain, so kernel of phi alpha is a principal ideal. So kernel of phi alpha is the ideal generated by a single polynomial Pt. This means that phi alpha of P is 0, i.e. P of alpha is 0. So what this means is that alpha is a solution to a polynomial equation where the polynomial has coefficients in f. So alpha is the solution, a solution of a polynomial equation with coefficients in f. Okay, in this situation we say that alpha is algebraic over f. Okay, so we say that an element alpha of K is algebraic over f if it is the solution of a polynomial equation with coefficients in f. The second case is where kernel of phi alpha is trivial. In this case, for every polynomial Pt, so we're looking at polynomials with coefficients in f. For every polynomial Pt in Ft, P of alpha is non-zero. Okay, in other words, the substitution map is injective. In this case, we say that alpha is transcendental over F. Okay, so we have two kinds of elements in a field extension. Either an element is algebraic or it is transcendental. Now note right off one simple fact that if alpha is in the small field F itself, if alpha belongs to F, then take Pt to be T minus alpha. Right, that's a polynomial in Ft because alpha is in F. And so we have phi alpha of T minus alpha. Well, that's alpha minus alpha, which is 0. So every element of F is algebraic over F. And so the only interesting question is, when an element is not in F, is it algebraic or transcendental over F? Let's look at some examples. So the simplest example would be to look at the complex numbers of the real numbers. That's field extension that we are all very familiar with. So look at complex numbers over real numbers. And now we have some alpha belong to the complex numbers. We can assume that alpha is not in the real numbers. So let's assume that alpha is a complex number that is not a real number, which means that alpha is not equal to alpha bar. Okay, and is this alpha going to be algebraic or transcendental? Well, I claim that alpha is algebraic. We'll find a polynomial with real coefficients that alpha satisfies. And that polynomial is, well, if you're used to solving quadratic equations, you can easily guess what the polynomial is. Let Pt be the polynomial T minus alpha into T minus alpha bar. Okay, now this polynomial is T squared minus alpha plus alpha bar T plus alpha alpha bar, which I can also write as T squared minus 2 times the real part of alpha times T plus the absolute value of alpha squared. So this is a real number and this is another real number. So that, and alpha obviously satisfies this polynomial Pt because alpha is one of its roots. So therefore alpha is algebraic. So every complex number is algebraic over the real numbers. Let's look at another relatively simple example. Let's look at the extension fx over x f, and let's take alpha equal to x itself. Then for every polynomial ft belonging to ft, phi alpha of ft is just, you're substituting f of x for alpha, and so this is just an element of fx, and this is not equal to 0 unless f of t is 0 is identically 0 as a polynomial, and so x is transcendental over f. Okay, now let's come to a slightly more interesting and in some sense, still very active area of inquiry, interesting example, which is to look at complex numbers over rational numbers. And we ask, can we find transcendental numbers? Here, are there complex numbers which are not algebraic? Okay, so in this context, so if alpha belongs to C, is called an algebraic number, if alpha is algebraic over Q. And it's called a transcendental number otherwise. So given any complex number, you can ask, is it transcendental or is it algebraic? Now there's a very simple counting argument which shows that there must be lots of transcendental numbers and that algebraic numbers are in fact quite rare. In fact, algebraic numbers are countable. The set of algebraic numbers is a countable set, but the set of complex numbers has cardinality, the continuum. It's an uncountable set. And so there must be lots of transcendental numbers. How do you see that? Well, I'll just sketch the steps in the proof. So firstly, we start with the fact that, which you all probably know, that Q, the set of rational numbers, is countable. Right? So that means that Q to the D is countable. Which means that polynomials of degree D, they have D coefficients, each come from Q. So the set of polynomials of degree less than or equal to D is countable. Which means that the set of all polynomials with rational coefficients is countable, because a countable union of countable sets is again countable. Now, each polynomial has only finitely many roots. So, given any algebraic number, we can associate to it one of the polynomials of which it is a root. And this gives a finite to one map from algebraic numbers to polynomials in Q. So there is a finite to one map from algebraic numbers into a countable set Qt, polynomials in one variable. Therefore, there are countably many algebraic numbers. And hence, there are uncountably many transcendental numbers, because the complement of a countable set in an uncountable set is still uncountable. There are lots and lots of transcendental numbers, but it turns out it's not so easy to prove that a number is transcendental. So the first well-known number to be shown to be transcendental was pi. Pi is transcendental. And this was proved by Hermite in 1873. Then Euler's constant E is transcendental. And this was proved by von Lindemann in 5 years later, 1882. But to this day, it's not known whether pi plus E is algebraic or transcendental. So while we know that there are lots of transcendental numbers out there, it's difficult to show that a given number is transcendental. And let's look at a more concrete example, okay? So square root 2, so let's say alpha equals square root 2. So is this algebraic or transcendental? Well, this one's easy, because if you take pt equals t squared minus 2, and then you substitute square root 2 here as a solution for this equation, then p alpha equals 0. So square root 2 is algebraic over q, hence it's an algebraic integer. So square root 2 is algebraic. What about square root 3? Well, now you can take pt equals t squared minus 3. Maybe we'll call it qt. Then we have q alpha equal to 0. So square root 3 is also algebraic. Well, in the spirit of pi and d, we can ask, is square root 2 plus square root 3 algebraic? In a later lecture, we'll see a very conceptual reason why square root 2 plus square root 3 is algebraic. But right now, let's just try to find a polynomial for which square root 2 plus square root 3, a polynomial with rational coefficients for which square root 2 plus square root 3 is a solution. So look at this gamma. We want to find a polynomial such that gamma satisfies this polynomial. So gamma minus square root 2 is equal to square root 3. If we square that, we get gamma squared minus 2 root 2 gamma plus 2 is equal to 3, which we can rewrite as gamma squared minus 1, I guess, is equal to 2 root 2 gamma, and then we can square that again and we get gamma 4 minus 2 gamma squared plus 1 is 8 gamma squared, and so we get gamma 4 minus 10 gamma squared plus 1 is equal to 0. So there you go. There's a polynomial of degree 4 that with rational coefficients that is satisfied by square root 2 by square root plus square root 3. So square root 2 plus square root 3 is also algebraic.